Last time we looked at a little bit of critical angle type stuff, kind of a specialized form of refraction situations. We'll practice that a little bit. I want to show you a couple other things that are connected to the refraction and critical angle stuff you guys have been looking at a little bit. So let's just start with a critical angle type situation and see what we can do here. So let's start with a situation where we've got, let's start with a boundary of some kind, so we go a little boundary, and let's say this here is, this is glass, and we've got some light coming in, so here comes our light, and the light comes in and it internally reflects. Okay, so it internally reflected, and let's say that it came in at let's go with 40 degrees. Okay, all right. Now, I would like to know if we can figure out what is the speed of light in that first material. Now, of course, to know that, it'd be really, really handy to know its index. So I can use the critical angle stuff we were working on to figure that out. I know that sine theta c is going to be n2 divided by n1. Now I know the index for glass, that's the 1.5. We've used that before. The only thing I don't know is my n1. So my n1 is just going to be my n2 divided by sine theta 2, and I can solve for it. And I know that index has to be more than the 1.5 for the glass because you have to start in the higher index material. All right, so if I do the calculation, I get an index of around 2.33. So actually really close to what diamond would be. Okay, now that I have the index, finding the speed is relatively simple. Speed in the first material would be c divided by n1. So I'll just take my speed of light in a vacuum and divide it by the index. And we're looking around 1.29 times 10 to the 8 meters per second. Okay, so there's a little practice with our critical angle and basic calculations with that. Okay, so now let me see if I can show you a few things involved with the refraction and critical angle stuff you guys have been working on. Okay, so this should look familiar to you. There's that little light beam thing we've used before, and we've got our shining through. Of course, a lot of people know it's a good old-fashioned prism, and of course, prisms are known for making rainbows. And the actual creation of color and getting color out of light has a ton to do with refraction and critical angle and that type of stuff. So here I've just got my beam of light, my red light going through the prism, and it bends or refracts twice, changing angle twice. And I'm going to change the color. And watch what happens when I change the color. As I change the color, you can actually see that the beam actually changes direction a little bit. It doesn't actually go straight. And that's why if I switch it to white light, which is a combination of all the colors put together, that's where you get the rainbow effect from. Because different colors interact with the material in different ways, and that's how the colors are extracted out based on their interaction. So we are going to look at this a tiny little bit. So this is where we get colors from. It's usually from a combo of good old-fashioned refraction and critical angle, one or the other combinations of the two. And the prism is a great example where you have the prism, something like this, okay, and we have the light coming in. And when light goes in, it will spread into colors. And the red one, if you don't remember, the red one actually went the straightest, and the bluey purple type stuff actually bent the most. And then we've got all the other colors in between. Okay, so the reason why they spread out like this is red light actually has the longest wavelength. You're looking around 700 nanometers, where blue light has got the shortest wavelength. You're looking around the limit around 400 nanometers, because you can see between 400 to 700. So since they have the shortest and the longest wavelengths going on, they interact with more. So the longer one, the red light, might look like this, where the blue light might look like this. So this one here, the red light, actually ends up having less interaction, is a good way to think of it. So there's sort of less effect. And the blue light would be the exact opposite. It wiggles around there so much, there's much more interaction, it will refract a lot more, and that's a nice way to think about how this actually works. And this is how they actually work. So this is an idea of using refraction, and this is how prisms work to actually separate the light. Okay, now prisms aren't the only way to actually get light, or to get light to change colors. Another really common one here, little image, is rainbows. Now, rainbows work actually a combination of internal reflection and critical angle, where you have little droplets in the air, and light comes in, that's the white light coming in, it refracts, and the refraction acts like a prism. The droplets actually act like little tiny prisms, which split the colors and start breaking them apart. They then hit the far side of the droplet. That's where total internal reflection kicks in and has it come back the other way towards you are. That's typically why if you're looking at a rainbow, if you're looking forward at a rainbow, the sun is typically going to be behind you because the light from the sun comes from behind you, hits the droplet, goes into the droplet, and then internally reflects and comes back towards you. And based on the geometry and the position of the droplets, that gives you different angles, and depending on your perspective and how you are set up with different angles, you will then see different parts of colors coming from different droplets. All the droplets are giving off all the colors, but it's based on your location in terms of which droplets are giving you which colors based on where you are. Another common place to actually see colors and stuff like this is what's called thin film interference. This is especially when you see like oil and stuff like that on roads and it rains a little bit or something like that, or sometimes like in saran wrap or bubbles on water. It doesn't matter. It's all little things like this, where light comes in and it goes through the first boundary and it refracts. But some of it also reflects, and some reflects, some refracts. Then the part that keeps on going hits the second boundary, and part of it can refract, and some of it can reflect. Now, the thing is, the key is the double reflection. When you have like the two or more reflections going on, because when the light was coming in, it was all perfectly synchronized as white light. Everything canceled off. But when you have them separated, and one has traveled a little bit farther before it was reflected, when those two reflected beams come back, they're no longer perfectly synchronized anymore, so they don't perfectly cancel out anymore, and that is why you start seeing colors come out of it, because not everything's canceling off perfectly. That's why when you often look at these things, the colors are often moving and shifting, because the thickness of the layers is changing, so there's different amounts of offsetness between the waves and stuff like that. But that's sort of how that works. You can even see the combination. One of the cool things you can see it. Sometimes it's very rare, but you can actually see this effect in the smoke or exhaust trails of planes. And the exhaust planes actually, it acts like a rainbow type thing with little tiny particles of vapor, and you can actually see a rainbow type effect as the stuff works. Okay, so these are other different common ways to find colors and stuff like that. So if we go back to this, so we can also get colors from things like, not rainbows, but rainbows. Okay, we've got good old-fashioned rainbows. Okay, and basically those little tiny droplets sort of act as prisms in order to break apart the actual colors. Okay, they actually act as prisms to actually separate the colors, and then it internally reflects. So you get internal reflection afterwards. Okay, we can also get colors from what's called thin film interference. Okay, and this is when we have things like oils and that kind of stuff. So what we have are these multiple reflections. These multiple reflections don't actually cancel, and because of that you get individual colors coming out. Okay, so it's kind of neat, especially like soap bubbles and that type of stuff, especially when the sun hits them, or a nice little oil droplets and stuff like that on water in the streets and stuff like that. Okay. Now there's one other really, really cool type of internal reflection type or refraction type thing that I'm going to show you as well. So another really cool effect or observation of this is what's called a sun halo. And this is kind of restricted to cold climate type areas like where we live. And we have ice crystals in the air. And those little ice crystals in the air act like little prisms to actually refract the light coming from the sun, which causes it to create sort of like a halo type effect. And this is a pretty cold climate going on right here. And this is called a sun halo. So it's kind of cool. If we sort of look at what's happening, we've got the sunlight comes in and it can go straight towards you, and that's of course why you see the sun. But some of the light will hit these crystals that happen to be right here, and they will refract inside of it and come towards you. So it looks like there's like a ring of light around the sun when it's actually coming from the sun and then being bent around. Another more common one is actually what we often refer to as sundogs. And here's a nice picture of sundogs where actually, you have the sun right in the middle, and actually it looks like there are like mini suns on the left and right. Now this one's actually producing almost a nice halo. You got sort of like a bright spot above it as well. You can sort of see a ring structure around it. Typically you need this to be on a nice calm, really, really cold morning, like super cold. There's nice crystallization going on in the air. You want wind, nice and calm, nice and cold, and you can see this. This picture was actually taken very, very close to our school a couple of years ago. It was a really nice cold morning, and went past an area, and I took this picture. I was going past an open area where there's like a water retention lake type thing going on, and it was beautiful, beautiful sundogs out, super bright. And you got to look at, typically in the morning on the way to school is when you can often see them. And it has been a nice, cold, calm night, and it worked out really, really well. So this was actually taken really close to our school. So sundogs and sun halos are just a wonderful natural visualization of the whole refraction idea. There's internal reflection involved, the whole bit, all the stuff that we've been talking about. It's really kind of cool. Nice natural phenomenon that happens all the time.